in this lecture, we're going to start putting together some of the pieces that we've covered in the last couple of lectures and start to see how this is going to lead us to finding black holes and deciding that they really are black holes and not something like a neutron star. Now, what we commonly know if we are doing real astronomical observations is, well, first off, we're going to know the velocity because we can always do the Doppler effect. That's a pretty straightforward thing. We can find the velocity. Also, you're either going to know A or P. You're either going to know the semi-major axis of the orbit or you're going to know the orbital period. Most of the time it's the orbital period because it's relatively easy to watch something going around in a circle and time how long it takes to do that. And it turns out that these three values are something that are related to each other. If we imagine, let's pretend for a minute that the orbits are actually circular instead of ellipses. Now this same logic turns out it to be okay for ellipses as well. But let's pretend we've got something that's going around in a circle. So there it is, and it can go around in the circle like that. And this circle has a radius of a because that's the orbital radius of the object. If we think about what distance does it go in one time around, well, that's the circumference of the circle, which is 2 pi a. How long does it take to do that? Well, that's the definition of the orbital period, p. So if I think that the speed is the distance divided by the time, well, that should be the circumference, 2 pi a divided by the period, p. So v is equal to 2 pi a over p. So supposing that the information that I knew was the speed and p, I could calculate a and then plug that into Kepler's third law. So that's going to be our next step. And then finally at the end, we're going to put this together and actually find v using the Doppler effect and so on. So this will turn into a big giant problem in the end. So here's an example. So I'm going to find the mass of the moon this time. Now we're going to use a satellite because there's nothing natural that orbits the moon. You've got to have something that orbits it to find its mass. So we're going to have this satellite. It's going to go around and orbit the moon at 100 kilometers above the surface. Now it turns out that the value of a that you want is actually the distance from the center of the central object, and that's relevant in this case. So I just sort of looked up the radius of the moon and added 100 to that. So my value of a that we're going to use is 1,840 kilometers. And we have a speed that's given to us. We're going to find the mass of the moon. So the first thing I'm going to do is I'm going to take that a and I'm going to convert it to meters because that's not good units yet. So there's 1,000 meters in 1 kilometer. So this is 1,840,000 meters. Now before I can use Kepler's law, I need to find the orbital period. So this is where this new equation, v equals 2 pi a over p, comes from. I've got 1,628 is v, 2 pi times, let's call this 1.84 times 10 to the 6th. Divided by p. Again, I would encourage you to do this on your calculator yourself. Make sure you know how to plug in the numbers correctly. I'm going to do the math. So I get a period of 7,098 seconds. And now I'm in a position to use Kepler's third law. Because now I know p, I'm going to ignore the mass of the satellite because the satellite is very small compared to the moon. So I can say that 7,098 squared equal to 4 pi squared over g times the mass of the moon. times 1.84 times 10 to the 6th cubed. So comes, let's see, 5 times 10 to the 1, 2, 3, 4, 5, 6, 7 equal to 5.9 times 10 to the 11 over m times 6.2 times 10 to the 18. Oh, do the math. And we get the mass of the moon is about 7.4 times 10 to the 22 kilograms. You can check that in the back of your book. That's reasonably close to correct.